Thank you. Southern Observatory, or simply ESO, its acronym. My name is Farid, and with the producer Hector Salas, we are going to be your guides during this trip to the ESO Paranal Observatory. So just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010, and I have been working also for an astronomy center in a university in Antofagasta. And regarding my personal hobbies, well, astrophotography is one of them. Well, as I told you, I am not alone. I am with the producer Hector Salas. How are you, Hector?
Hi Farid, happy to be here once again. So my name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work with topics related to the circumgalactic medium. You can think of this as the environment that immediately surrounds galaxies. And I have been a member of the team of guides for Paranal Observatory since 2019. I started while I was doing my master's degree in the University of Antofagasta. And today I'm the producer. So I will be changing the pictures and videos, but I will also be reading all your comments and questions. So if you have any doubts or if you want to send us greetings or anything, just write it down in the comment sections. And we'll have a couple of minutes in the tour for answer any questions you might have. So please go ahead with that.
Okay, thank you very much, Hector. So, well, ESO wants to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So please remember, we will have some time to answer questions later. And also you can share this experience if you want with your friends using the sharing buttons on Facebook or YouTube. So we are going to start immediately. And the first thing I am going to do is to help you understand the place of our visit. So we will begin with some information about the European Southern Observatory, or ESO. ESO is composed of 16 member states. Uh, we will have a picture to talk about that. The headquarters of ESO are located in Germany. Also, Australia is one of the strategic partners of ESO, and Chile is the host state and home of all ESO observatories. From the 60s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories such as ESO to our country. As a result, Chile offered its territory and ESO did choose the more suitable areas. Do we have the picture, Hector, about the member states? Okay, thank you. So the mission of ESO in this case is to design, build, and operate astronomical observatories. And why? Well, to enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. Right now, you are looking at a picture with the three observing sites of ESO in Chile. So we have the Chajnantor Plateau. This is the site of the ALMA radio telescope. So ESO is part of this very important place for radio astronomy alongside other international partners. In addition, south of the Atacama Desert, at 2,400 meters above sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT or the 3.6 meters ESO telescope. And this one is using the HARPS instrument. This instrument is an exoplanet hunter. And finally, we have the place of our visit, the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT. This is the most advanced visible light telescope on the planet. In the next few years, we will also have the Extremely Large Telescope, or ELT, and this will be the biggest visible light telescope on Earth. Also, near Paranal, we will have the CTA, the Cherenkov Telescope Array, an array of telescopes focused on capturing gamma rays. Okay, so now we have a better picture, so let's travel to the Paranal Observatory. We will take a look at an animation. So virtually you will you are going to fly over the Atacama Desert in the north of Chile. Hector, do we have the animation, right? Hector, do we have the bit fly over?
I already put it. I'm seeing the flyover. I'm not sure if you're seeing it.
Okay, I'm not quite sure if we have the flyer, but let me take a look first. Okay. Okay. Thank you. So it's okay. Don't worry. You can just let me know. Okay, so we are basically flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago, and specifically about 130 kilometers south of the capital Santiago.
Okay, since we lose Farid for a minute, a little bit. Uh,
Okay, sorry, I just came back.
Okay, you can back. Okay, you can
Can
continue.
can you hear me, Hector?
I can hear you.
Yeah.
Yeah.
Okay. So, okay. So sorry. I am not sure what was the last part you say, but uh, basically in this final uh, picture, we are looking at the Paranal telescopes in the mountain, and we have a cloud cover uh, behind the telescopes. So the clouds over there are, as you can see, isolated. I mean, are far away from the observatory. We are 12 kilometers away from the coast, and the mountain top is at 2,600 meters above sea level. So the ocean is basically below of the cloud cover you can see over there. And why those clouds if right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt stream. This is a cold stream near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level. In this case, this phenomenon is helping to keep low the cold, humid, and basically bad air for astronomy. But about the layer, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. Now, clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surfacing 2,000 meters above sea level. So we have other natural barriers in this area. About 200 kilometers to the east, we have the Andes Mountains with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. But also, we are far away from artificial light sources because of human activity, I mean, light pollution. So, overall, this is one of the best places on Earth for astronomical observations. So, in this animation we can see right now, you can see that this is not an ordinary mountain, and we can see the different telescopes and structures in the mountain. We are in the summit of Cerro Paranal. Okay, so this view, of course, is very impressive, and in this case, as I told you before, the atmosphere is extremely quiet. So this observatory is a true oasis, and you will see how in one of the driest deserts we have a lot of life, but also we have a lot of science. Okay, okay. Let me share my screen, or do you want me to share my screen, Hector?
Already have mine ready as a backup if you cannot share yours.
Okay. Okay, thank you very much. Let me just take a look, and I will um um
Okay, that's your
okay.
screen.
Okay, yeah, you can keep your screen just in case. Thank you.
Hmm.
Okay, so in front of us we have the Very Large Telescope, or VLT. Okay, it's acronym. So if you see the amount of buildings, we have four giant domes and other small and rounded ones. I mean those ones. Okay, so you can see that we have several telescopes in this mountain top. Okay, so it is clear that the Very Large Telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. Okay, so let's take a closer look. Here you can find the four unit telescopes, or UTs. Okay, each one with a primary mirror of 8.2 meters of diameter. Okay, so the giant ones in your screens Each telescope has a primary mirror of 8.2 meters in diameter. And the other small ones, those ones, are the auxiliary telescopes. Okay? The auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters of diameter. Okay? So you can see that we have one here, and we have two others there. So we have 4 auxiliary telescopes. Now, regarding the UTs, the big ones, each UT has a name in Mapudungun. This is the language of the Mapuche people from the south of Chile. So here we have Antu, and Antu means sun. This one is Cuyen, which means moon. This one is Melipal, which means 4 stars, but this is a reference to the Southern Cross constellation. And this one is Jepun, and Jepun is a reference to the planet Venus. Okay, so these are the names of the different telescopes. And coming back to the small ones, the auxiliary telescopes, they are very special. Okay? Those small white telescopes are very special because they are mobile, and they can be moved using a rail system up to 30 different positions. So you can see this rail system, right? And you can see something like a station in the ground. So basically we have 30 stations, and all connected by this rail system. Um, so the main purpose of this is that we can change the configuration of the auxiliary telescopes, and we can place the small ones in any station we want, so they can be in a more compact or more extended configuration. Okay, so they were specifically designed to work all together as a single big telescope with a variable diameter. In this case, able to reach up to 200 meters. So we are going to explain a little bit more about this with an animation. In this animation, we can say that the technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. Now, thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during the travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. So essentially, in this animation, you can see that the telescopes can combine the physical light using underground tunnels. So the physical light will travel in the underground tunnels, and this light will reach at the same time a single point of combination in the facility located in the center of the platform. So this is the interferometer builder. So we can do this with the 4 small ones or the 4 big ones. Okay, so interferometry is what makes Paranal the most advanced optical observatory on Earth. Okay, so we will come back to the tour screen, and now you will have the opportunity to visit one of the telescopes. We are going to visit the UT3, or Melipal. We can't enter all the telescopes, but don't worry about that, because the 4 ones are identical in size and shape. So the only difference are the instruments inside. You can know more about the instruments, of course, if you visit the ESO website. Okay? Okay, so now we are going to access the UT3 Melipal, and you can you can notice immediately that this is a giant telescope, right? In this view, we are on the last floor of the telescope at the same height of the main mirror in front of us. I am going to do a close-up so you can you can take a look at the mirror here. This mirror is, well, it's very heavy. It's 22 tons with 8.2 meters of diameter and only 17 centimeters thickness. Created from a ceramic and flexible material. This material is called Observatory, and the surface of this mirror is a very thin layer of aluminum. Okay, so this is essentially the reflective surface of this mirror. So this mirror is not glass. Okay, it's a ceramic and flexible material, the Observatory, and the surface is a very thin layer of aluminum. Now, you need to understand that during the night, this telescope needs to be rotated. We need to point to different areas of the sky. So, because the telescope must be tilted, we need to incline the structure. You need to understand that the mirror is heavy, right? 22 tons. And the mirror, well, it's not an ordinary mirror, right? This mirror is concave, okay? It's like a spoon, okay? So when you have a concave mirror like this one that is so heavy, and you need to, tilt the telescope and point to different positions in the sky, just because of gravity or physics, the mirror could suffer some distortions, deformations. Okay, so this creates some kind of problem because the quality of the final picture will be affected. So we need to do something about that. We need to do something to prevent this kind of deformations, and in this way we can preserve the quality of the final picture. So in order to explain that, I will show you this telescope from another perspective, from this position down. You Well, now you can see that we are in a different level, right? And you are looking at the telescope from the underneath. Okay? So you can see this kind of cell here. This is a cell supporting all systems, assisting the mirror. So the mirror is basically on top of this structure, and here we have something very very special um, uh, that I will show you. I will do a close up to show you. We have those gray boxes. Can you see? We have this. We have this kind of device. So those objects there are actuators. They are they are a kind of piston, okay? And we have 115 total. The main mission of this is to compensate any distortion on the mirror when the mirror is tilted. So the mirror will preserve the concave shape, and the quality of the final picture will be always the same. Okay, so that's why we have those actuators. The actuators are essentially part of a technology developed by ESO, and this technology is called active optics. Okay, so the active optics system is helping the Paranal telescopes to preserve the same quality of the final picture. As I told you, this technology was developed by ESO, and it was operated for the first time in La Silla Observatory, in the New Technology Telescope, in the NTT. Okay. Now, regarding the actuators here, the last information I can tell you is that we have 115 total, okay, controlled by a computer. And so that means that we don't need an engineer or someone manipulating the computer, the actuators. Everything is automatic. And of course, it's a very important technology because uh, we need to keep the optimal shape of the concave mirror, because otherwise it could suffer deformations just because of gravity physics. And those deformations, imperceptible in a first view, could be critical in the result of the observations. Now, how is this working together? How the telescope can receive light and how can we observe this light? We will show you a short animation to explain that because you need to understand how this telescope will receive light. So the first step, the first thing is that we need to open the dome. Okay, we need to open the dome. In this view, of course, this is exaggerated, and the primary mirror will receive light in first place. This light will be concentrated and will be reflected to a secondary mirror in the top, and then the light will be reflected again down, and the light will be reflected in a tertiary mirror. So this tertiary mirror will reflect the light to one of the instruments. We have actually three instruments. You can see this kind of red, blue, and green squares. This is just a representation of the instruments. So we have one instrument at both sides. Sorry, I mean we have one instrument here. We have another instrument in the other side. We have another instrument in the base. Okay, so we have three possible instruments, and we can use only one instrument per time. But regarding the animation, well, you was able to look at the primary mirror. This is the secondary mirror. This is a convex mirror, and the tertiary mirror is located in the middle. Okay, but it's not visible here because well, this is blocking the view. But the tertiary mirror is flat. Okay, and regarding the instruments, well, essentially the instruments are um, very big and complex machines, right? And you need to do a permanent calibrations, maintenance, you know. So that's why, for example, in this picture, we have some engineers working. Do you see them? They are working every day in Paranal to do some maintenance, to fix some problem. So basically, they are here to prepare the telescope and the instruments for the next observation night. Okay, so that's why we have people here. But during the night, no one is here. During the night, everything is in darkness, and the telescope is empty. No people is here because everything will be controlled remotely from a control room. Okay, so and this will be actually the next stop of this visit. We are going to visit the control room of the Paranal Observatory. Okay, okay. So this is what happens here. This is essentially the explanation of this telescope. So now we are going back outside because now, as I told you before, we are going to visit the control room. This building here is what we call the control building. Okay, as you can see, it's in the mountain top, but not at the same level of the telescopes. I can show you another view to understand this. This is the control building from this from the opposite view, and here we have the control room of the observatory. But before going there, I would like to know if we have some questions from our visitors. Hector?
Okay, so we have a few greetings. We have Max says hello. We have Anita says hello from Romania. And we have greetings from Antofagasta as well, from Jorge. But we don't have any questions so far. So let me ask you one of the usual questions that we receive in the in-person tours. What kind of maintenance is necessary for the telescopes?
Well, yeah, this is actually a very frequent question. So, well, essentially, the mirrors are the most delicate, the most important part of each telescope. So, in order to keep the mirrors in optimal condition, we need to do two kinds of maintenance. Okay, one is something like an easy maintenance in order to clean the mirror. So for this easy maintenance, let's say that we need to rotate the telescope a little bit, and we have an engineer to spread a carbon dioxide snow on the mirror. This is something like a foam. So this element will remove dust from the mirror because we are in the middle of the desert, so we have dust in the environment. So this carbon dioxide will remove dust, and because the mirror is rotated, the dust and the carbon dioxide will fall to the ground by gravity. So this is like the easy way to clean the mirror. But we have another way, and this is more complex, and we need to do this every 2 years. Essentially, we need to remove the entire mirror from the telescope. I mean, we need to remove the mirror and the white cell. In order to do that, we need to extract the mirror with some cranes. There is a door here, and in order to understand this better, I can show you from this view outside. If you pay attention, you will see something here like a yellow structure, right? So we need to place the mirror in this something like a platform, and at the ground level, we have a vehicle waiting for the mirror. So once the mirror is here, we need to drop the mirror very, very gently, of course, to this vehicle. And the vehicle is coming, is going to the base camp, and because we need to transfer the mirror to another facility, to the mirror maintenance building. So in that place, the mirror will have a recoating. A recoating is essentially to remove the aluminum layer, and then we can put a new one. So essentially, when this process is finished after 3 or 4 days, the mirror will look like a new mirror again. Uh, I mean, we are not replacing the mirror structure. We are not replacing the main mirror cell, okay? The main the ceramic and flexible mirror. We are just replacing the uh, aluminum surface. Okay? This is a very thin layer of aluminum. So after we do this, we need to transfer the mirror again to the mountain top. We need to reinstall the mirror in the telescope, and the telescope will be ready again for observations. So that's what's happening regarding the maintenance, in this case of the mirrors.
Okay, thank you. Maybe before we continue, you can tell our viewers about how to visit the observatory in person.
We have tours in person every Saturday at 10 a.m. and 2 p.m. But in order to visit Paranal, you need to do an online booking, maybe 2 weeks in advance. You need to access the ESO website, and you can find a section that is called the weekend visits, weekend public visits. So you need to find a Saturday that is good for you, and the visit is totally free, but you need to arrive to the observatory with your own car or transportation. Um, the closest city is Antofagasta, and it's about 1 hour and a half travel time. But it's always better if you plan ahead and you start your trip 2 hours before to arrive in advance, and then the tour takes about 2 hours and a half, and you will visit the telescopes during the day, and you will have an explanation of everything there. So this is a very, very good opportunity to visit this observatory. We have tours in Spanish and English. So we of course recommend that if you are in the area, you can try to book a visit to Paraná.
Okay, thank you, Farid. And I'll remind our viewers that we'll have a second round for answering questions later on. So if you have any doubt or any question about the observatory or about astronomy in general, please send them through the chat.
Thank you, Hector. So now we are going to continue, and the next stop will be the control building, specifically the control room of the observatory, because from this location, we have the scientists, we have the astronomers working there. So let's take a look now, because this place is, well, as you can see, is not a super futuristic place. It's just an office space, but of course, all the science happens here. So you have different, workstations like this one. Each workstation is dedicated to the remote operations of one single telescope. So this workstation, for example, belongs to the Melipal telescope. Okay, so all operations with Melipal are controlled from here. So you can see we have different computers for different purposes. We have some people working here. So they are working only on the Melipal telescope. Now, if we look at the other workstation in front, we have this one, and this one belongs to the UT4. The UT4 is Jepun. Okay, so again, we have different computers for different purposes. We have some people working. They are, well, you need to understand that during the night, they are working all night from sunset to dawn. Um, and uh, and we don't need a lot of people actually, maybe about 15 people, something like that, um, because we usually need only one astronomer and one telescope operator. So essentially, as you can see, with piece of space, here I can show you the remaining workstations. This one, for example, is for the UT1 and 2. So the same, we have different computers here. We have some people here. So in order to understand what is the main purpose of this control room, well, you need to essentially understand that from this place, um, we can do the remote control of everything. Okay, so all the systems, all the telescopes, the instruments, everything is controlled from here. Okay, so I will show you this workstation here. This workstation belongs to the last telescope. This is for this is for Guyen. Yes, and you can see the same configuration. You see. But we have, for example, this person here is a telescope operator. Okay, so in Paranal, in the control room of Zero Paranal, you have a telescope operator, and the telescope operator is essentially the person. It's like the pilot of the machine, because it's the person in charge of the technical details and the movement of the telescope. So he can control where the telescope is pointing, where the telescope is observing at night. And this person is working with an astronomer. Let's suppose this person is an astronomer. So the astronomer is in charge to direct the scientific observations, and this person will decide the next steps. So this person is something like the co-pilot. Okay. The observations, of course, are performed by experts from ESO for scientists from all the planet. Okay, so that's it. This is what happens here. So now I want to go outside again, because I would like to show you something very, very interesting for all of you. Is essentially a list of the top 10 discoveries from the ESO sites so far. So please pay attention, because now we have something very, very interesting for all of you.
Observations with ESO telescopes have led to many breakthroughs in astronomy, and over the years have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at Lucia was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam, or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at Lucia and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so we hope you liked the top 10. This was only a fraction of the discoveries, thanks to the ESO telescopes and the scientific stuff behind them. Very, very impressive. So now we can continue, and from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So as you can see, the sky is almost completely dark, with the last traces of light from the twilight. The moon is below the horizon, and the sky is full of stars. So we are going to explore some interesting areas around here. And the first thing I want to show you is a very popular constellation just about the AN2 telescope. I mean this one. So if we go up, we will find the Orion constellation, this one. So let me do a close up, and we can see Orion. Okay. So in the mythology, Orion represents a hunter, and you can recognize this constellation because of those three stars somewhat aligned, representing Orion's belt. And inside of Orion, we have another very interesting object. We have the Great Orion's Nebula. This is very interesting because this object is it's very big, it's very bright. You can even see this object from with your naked eye in a dark and clear night, of course. But it's possible to observe this object. It looks like this distorted spot in the sky. But of course, you can observe also with binoculars or a small telescope, and it's very, very impressive. Okay, so and also, and Orion is visible from the northern hemisphere and the southern hemisphere, so everyone can essentially observe Orion. Well, we're going to change the position and move to the brightest star in the sky. We are going up a little bit, and we are going to find this bright star. This star is called Sirius. This is the brightest star of the night sky, and this star belongs to the Canis Major constellation. And this one is representing Orion's one of Orion's hunting dogs. So at this point, you need to understand that the constellation of the brightest star in the sky is connected in the mythology to Orion. Okay. Now, I want to show you something else, because if we go down again and we find the AN2 telescope, you can see that just next to AN2 here, we have another interesting object. This one, we can see the Pleiades. The Pleiades is an open star cluster located in the Taurus constellation. If you have a dark and clear skies, you should be able to see at least 7 of them. Okay, that's why in the mythology they are also called the Seven Sisters. Okay, okay. So this is a open star cluster here, and now I want to show you something, because if you look carefully to this area of the sky, you will see that there is some bright and let's say a more concentration of stars here. We have a more dense and populated area with the stars in this part of the sky, if we compare with this area, for example, or this area. So essentially, when you are looking at this, you are looking at one of the Milky Way arms. Okay? And the Milky Way is our galaxy. Our sun is only one among hundreds of millions of stars in the Milky Way. Now, during the winter, in the southern hemisphere, we can see the center of the Milky Way. And this is another area full of stars between Scorpius and Sagittarius. So essentially, from the southern hemisphere, this this area of the sky is very, very beautiful because you can see all the Milky Way, including the center of the Milky Way online. Okay, now we are going to change the position because I want to focus on something else. I want to show you this, and because now I think you can see we have those spots in the night sky. Now, what are those spots? This one here and this one here are the Magellanic Clouds. Okay, this one is the large Magellanic Cloud, and this one is the small Magellanic Cloud. Now, they are not clouds; they are galaxies with an irregular shape. Both are visible only in the southern hemisphere, but you can see them with your naked eye in a clear and dark night like this one. This name, the Magellanic Clouds, refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people have no idea about what a galaxy is. Okay. Now, next to the Magellanic Clouds, we have something else. We have the smallest constellation in the sky. We have the Southern Cross right here. Let me show you. This one is the smallest constellation in the sky, Southern Cross. In this picture, you can see that Southern Cross looks tilted because, well, it depends on the time of and your location to see the Southern Cross in a certain position. In this case, you can see it's a little bit tilted, and the Southern Cross is also very important because it's a very good guide to find the South Celestial Pole. What is the South Celestial Pole? Is essentially a projection of the South geographical pole in the sky. Now, in the Southern Hemisphere, we don't have any bright star near the South Celestial Pole, near this projection of the South geographical pole. In the Northern Hemisphere, the northern observers, they have Polaris. Polaris is a very bright star near the North Celestial Pole, but in the Southern Hemisphere, we don't have any bright star. So the solution is, for example, to use the Southern Cross, and in this case, you need to project 4 times and a half in your mind, of course, the longer stick of the Southern Cross. So you can do that, and you need to project in using, I don't know, your hand as a reference, for example. You can project 1, 2, 3, 4 and a half, and more or less like here, approximately, we have the South Celestial Pole. That means that if you take an astrophotography toward this area, you will see a lot of circles, okay? Because this is a projection, as I told you, of the South geographical pole. Okay? And if you look directly to the ground, okay, from this point, I mean, if you outline a perpendicular line, you will look at the south cardinal point. Okay, so this is a good way to, for example, find your way if you are lost in the desert. Okay, so let's finish with this explanation of the night sky. Of course, it's very, very beautiful. You need to understand that this is one of the best places on the planet for astronomical observations. But now we are going to finish with something very special. We need to come back to the daytime because now I want to show you the residence of Paranal. So for this, I need to rotate the view and I need to point to the base camp, to the Paranal base camp, because in this location we have different facilities. We have rooms for contractors. We have the mirror maintenance building. We have offices for informatics, etc. So it's something like a mini city for all the workers. We have about 130 people working here. But the specific place I want to show you is the residence right here. So the residence is essentially a place where the ESO staff can stay and rest. Okay, so the residence is the home of the ESO staff during their when they are working in the desert. So in order to access this place, we need to use this ramp. This is the roof of the residence, and this place is not exactly underground. It's just taking advantage of the shape of the land. Okay, so in the other side is like a normal wall with several windows, but we need to access using this ramp, and you can see that the outside is beautiful. You have green areas, you have a swimming pool. So essentially, this is like the home of the ESO staff, as I told you before. It's like a hotel, but it's only for the staff. So you can find that over there we have the restaurant. All the people working in Paranal, they can go and eat there. We have the lobby, we have the reception. So is in this place we have 108 rooms, and it's full almost all the time. So this place, as I told you before, is for the engineers, for the astronomers, for visitor astronomers coming from another country. So all of them can stay here, and of course is a very nice and beautiful contrast if you compare with the desert in the outside. Okay, so we are going to finish here, and I don't know, Hector, if we have some last questions to answer.
We have a couple of comments, but not really any questions that we can answer at the point. So we have Jorge was telling us how he visited the site of the PLT construction at some points, and how he's impressed with how much it has changed since then. We also have Luis telling us how he did internship at La Silla a few years back, and now how he's a teacher and has an astronomy academy in his place. But not really any questions we can answer. So, given the time, I think we can just start saying our goodbyes. So, I would like to remind our viewers that we're doing these virtual tours every Saturday. We are switching between Spanish and English, and also between Paranal and La Silla observatories. So, keep an eye up when the next tour is going to be, which observatory, and in which language. And if you know anybody that might be interested in this kind of content, please let them know about it.
Okay, thank you very much, Hector. So, yeah, of course, we remind you that all this visit information and pictures are available on the ESO website, so you can navigate as you wish. And so I hope you like this virtual experience, and please stay alert to the ESO social networks to know when we will have the next virtual tour. So on behalf of ESO, I want to say thank you very much for your presence. Thank you and goodbye.